way we will get immune soon, inshallah.
Yeah. So we don't need the vaccine because vaccine itself is also another harm, right?
The vaccine is, I'm not very keen about this because so short time the vaccine, and
Yeah.
you're from biomedical background,
Yeah.
it's not really good because so many side and vaccine has to be tested for very long time, studied to see all the
Mm.
side effects and other things. So within 6-7 months, the vaccine, I don't know, there will be a lot of complications. I'm expecting that will those are giving, but people are
Mm.
now become like to release the
Yeah.
anxiety. They want to get something that can,
Mm.
but as a scientist, I think as a biomedical
Yeah.
and medical scientist, I think you know that the vaccine so fast you cannot really release. But what to do, because now the demand is so high and the
Mm.
pressure, under the pressure, I think the regulatory authorities also, I think they are forced to approve, even though they
Yeah.
don't want, but they are forced by the politicians and the government, I think, maybe. I don't know.
Yeah.
Anyway, let's pray just that Allah has protect us from the bad things like that.
Yeah. Inshallah.
Okay.
Yeah. So I think yeah,
Uh,
probably we can start now.
we
So
can
we
start.
don't want to waste any more time. Yeah.
Okay, I will
So I
start.
will please excuse me for like 15 minutes
Okay,
and I
okay,
will be
okay.
back.
And Dr. Irfan, I got a
Yeah.
mail from Dr.
Yeah.
Faid or Faid, I think, regarding the appointment letter. I got the appointment letter. Alhamdulillah. Thank you very much.
Yeah.
I
Yeah.
will send him
Yeah.
my, he is asking for my IC and some other documents. I will inshallah send
Exactly.
it.
Yeah.
Okay.
So
Okay,
I
but
decided that because we have quite some slot for this program because Dr. Alfi joined this program through pharmacy faculty,
yeah.
and then I decided to put you in faculty of medicine.
Thank you
So
very much.
because
Jazakallah.
we have to we have to finish that quota for
Mhm.
this month.
Okay.
So then
Okay,
it's
okay.
so
Thank you.
funny
Thank you
because
very
we
much.
now
Thank you
it's
also.
very difficult to
Yeah, because,
so then it's
thank
good
you very
that
much
you
to you and Dr.
okay.
Alfi to allow
Yeah,
have to get this opportunity. Inshallah, in future also I will try to contribute
yeah,
whatever I can with my expertise.
yes, definitely,
So thank
definitely,
you,
yeah.
brother Ikhwan. Maybe we can
Okay,
start with the
I see
student.
you, yeah, see you in
Please
15
join
minutes,
us back,
inshallah. Yeah.
inshallah. Okay, Assalamu alaikum. Putri.
Waalaikumsalam, Dokter.
So can I start now?
Yes, Dokter.
Okay. Before I start, I just wanted to ask you, have you all gone through my notes for the chromatography? Have you all got the notes? The one I sent for with Dr. Ifwan? Have you gone through those notes? Have you received the notes?
No, Dokter.
Uh, because I think in the Metabolomics WhatsApp group also Dr. Ifwan shared the file.
Oh,
But
yes.
anyway, if you didn't receive, please try to get the notes and then go through. And then if you have any queries, it's okay. Maybe you can discuss today or you can discuss later or you can email me anytime. Okay. So anyway, whatever you want to know, please check with me. Huh? I will be very happy to get you the feedback or whatever I can for you, inshallah. Okay, so I think I want to start now. Can you see the slides?
Yes, Dokter.
Yes, yes, Doctor.
Okay. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi.
Okay, a very good morning to everybody. Okay, those are joining today's lecture. So actually, this will be a bit continuation of my previous lecture on chromatography. Okay, so in chromatography, what we have seen that actually chromatography is a separation technique, and then we have discussed about liquid chromatography and gas chromatography, and also the liquid chromatography and gas chromatographic system. Okay, so in the system, we have also noticed that actually that after the separation, Okay, the chromatography give us a very good separation, but after that we need to know actually what are the things. So that's why we need to have a detection. Okay, so different types of detection can be, it can be very simple or very complicated. Complicated means actually high end, high end detection we can do just to know what are the things we have separated and what is their nature and how they looks like and how they behave, what is the chemical, physical structure, all these things. So on that aspect, actually, there are so many types of detectors available, but one of the most used and very critical and very useful detector, okay, is mass detector, okay, mass spectroscopy. Okay, so mass spectroscopy is a huge area of under the spectroscopy or what do you call in this field of spectroscopy. Okay, and this has been utilizing since quite early this 20th century or late 18th century or 19th century. Okay, but the excel, that means the things has been improved in the last 20 or 30 years, I think, is tremendously. Okay, and then your what we know about mass spectrometry is that it is a very good tool to determine the chemical structure, or to know the elucidation. When we do the structure elucidation, we can use this mass spectroscopy as an authentic tool. Okay, so the word mass, mass is referring to the molecular atomic mass. Okay, mass means weight. Is it what we know that what is the, we don't ask about weight about a person, is it? Because we ask about the weight, because weight is actually is a mass and the gravitational force we have to tell the gravity, but mass is the absolute. So when we use the word absolute, then we have to use the mass. So for the elements, you know that in the periodic table we have 105 or 108 elements in terms of the one. So we have this all the elements, you can see they have the mass, atomic mass. And then we have the molecule. When we have a molecule, just like we have water, is it? So we know hydrogen, the mass of hydrogen is 1 and mass of oxygen is 17, is it? That's what we know. So when we combine them, okay, so sorry, my weight of oxygen is 16. So when we combine water, H2O, it becomes molecular weight of water, the molecular mass of water is 18. Okay, so this is how we do the calculation of a molecule, and these are very accurately. So all this mass weight is given in the periodic table for each and every element. You will see they are very accurate, and then they never change. Okay, they never change. That means the hydrogen in Indonesia and hydrogen in Malaysia or hydrogen in America is the same weight we have to calculate. That means the water will be 18 molecular weight throughout everywhere. So that is the key things of this mass spectroscopy. Okay, so when we are talking about that the water molecule will be having a specific weight, so every water molecule should be of specific weight. So once we consider this, then we can go and do this for other molecules as well. Okay, so that is the things, the beauty of this mass spectroscopy, that we are using the weight, is it? So if we say that, okay, we have 10 students in this weight, in this class, okay, 10 students in this class, and then the average weight is 64 kilogram. Okay, so what does it mean? When I say that there are 10 students in this class, the average weight is 64 kilogram. That means, does it mean that each of the students will be 64 kilogram? No, definitely not. Is it? When we are averaging the weight, because we are taking the individual weight and then we are measuring them separately, and then we are averaging them, then we are combining them and divided by 10, then we get 64. Then we call this average weight. Okay, so when we go for individual, then we have to say this, okay, student A is 59.4, student B is 62.3, something like that. We have to do it individually. So same like here, that when we go for mass spectroscopy, when you go for atom, we have one weight, but when you combine them with the molecule, then they will be representing a part of the molecule. So when we have to consider, then we have to when we calculate the mass or the molecular weight, when you write down any molecular formula, you see the molecular weight, we go back to the origin. That means we go back to the element itself. Let's say you have water, you go back to the hydrogen, what is the molecular weight of hydrogen and what is the molecular of water, okay? And when you say carbon dioxide, okay, so what is the molecular weight of carbon, the nitrogen, what is the molecular weight of atomic weight of nitrogen? So we go back to there and then we calculate each of them and then we combine them. Okay, so the molecular weight is the combination of each and every atom's atomic weight. Okay, so from there, actually, the things is starting that the when we know that, okay, this molecule, we know that we can separate the molecule, is it? So water can be separated into hydrogen and oxygen, and this is now not a very big deal to separate the molecules into atoms or a smaller molecules. It is now possible actually by reaction, by other things, or a lot of things can be done to get into. But when you combine them, they should be giving a same structural formula or same molecular weight. Okay, so that's why when we call about this structural elucidation, what is structural elucidation? We elucidate the structure. We break the structure, we build a structure, and then we try to find out that the structure is giving a particular definite formula or the structure, the idea that is consistent. It's not getting changed. Okay, so when we do this structural elucidation, then we complement the spectroscopy is so mass spectroscopy or mass spectra become a very unique tool. So in like other like UVVs, fluorescence, all these they use the electromagnetic radiation for energy, but in this case we are not using any electromagnetic radiation, just like the absorption and emission spectroscopy. When we have the absorption like UV, IR, these are absorption spectroscopy. When we have the fluorescence, phosphorescence, then it becomes emission spectroscopy. So with this one they use the electromagnetic radiation, but this for mass spectroscopy there is no radiation has been used. Electromagnetic radiation has been used. It's just like you are weighing the molecule. You are weighing a molecule and the molecule has been cut into pieces. Is it? The molecule in the concentration, that's what we call them. That every piece will be carrying one charge, particular charge. Most of them, they will be having one positive ion. That's why the M is the molecular weight, the molecular weight of that particular part or the whole molecule, and Z is the charge. So we consider that one positive charge. So most of the time Z will be 1. So that will be representing anything divided by 1 is that particular number. So M by Z, that is the one with the unit will be used for molecular mass spectroscopy. So most of them, they will be referring to the molecular weight of that particular component or the molecule. Okay, so this is what we call the mass to charge ratio. M is the mass and Z is the charge. Z represents the charge. Charge is on the particular fragment or the part. Okay, this is the mass spectrum. Okay, so when we have the chromatography, we have chromatogram. Then whenever the spectroscopy, you have a spectrogram. So this is spectrum. So when we have the spectra, when you represent it is in a plotted form. Okay, mass to charge ratio against that means mass to charge ratio will be in the x-axis and the y-axis. Y-axis will be the abundance. Abundance means the population of that particular fragments. Okay, so then this is become a mass spectrum. Okay, so fragment the composition this chemical, and in the year 2002 actually Dr. Fenn and Dr. Tanaka, these two guys has developed the mass spectroscopy. Actually mass spectroscopy mostly was on the gaseous form, but these people, they has introduced for a what you call that for the bigger molecule like polymer, protein, peptides, and then also for the solid substance directly can be what you call used. Later on we'll see how these techniques can be adopted. Okay, so you see this very nicely. You see they put some is balance. Okay, they put some weight there. This is just a representation, and then the molecular structure on the balance. So accurately, the compounds has to be take it accurately. Huh? So the accuracy of the weight has to be there. So to identify the each and every element. So the output of the mass spectroscopy, the mass spectrum, will give you the information about the fragments and their relative the mass and charge ratio. Okay, so different will give you a different mass, which will be accurately weighted. Okay, which will be giving you an accurate output from the mass to charge ratio. Okay, because we are calculating back. Okay, just like I don't know whether if you everybody know about the pH meter. Everybody has used the pH meter in the lab or anywhere. So a pH meter actually is mainly is meant to measure the what we measure with the pH meter, measure the pH. And what is pH actually? pH is the hydrogen ion concentration. Is it? So we measure the hydrogen ion concentration in a particular solvent or in a mixture or in a buffer or in a water solution. Is it? So when we measure the pH, we put an electrode, okay, in the pH meter, okay, in the solvent, in the sample, and then we see that the display is showing the pH, like say 7.1. We say, okay, this is a neutral. If it is less than 7, we say, okay, this is an acidic. Okay, there's a 5.2, 3.5. These are acidic pH, and then when it goes above 7, 9, something, then it becomes basic pH. That means when we have acidic pH, that means we say this, okay, the hydrogen concentration is high, and then when it's basic, that means OH concentration is high or hydrogen is less. So the probe is giving us the information of the hydrogen ion concentration. But in fact, in reality, the probe is not counting the hydrogen ion. It is getting a potential difference between the reference electrode inside the reference solvent inside the electrode and the solvent it is put. So there is a potential difference, that means voltage difference between these two. Okay, this voltage difference has been calculated on the basis of the pH. So we are getting an information which is not an actual scenario, we are back calculating. Okay, so how we are getting this? We are calibrating the pH meter with buffer. So we are giving an information that, okay, for acidic buffer, this is the voltage. For neutral buffer, this is the voltage. For basic buffer, this is the voltage. Okay, so from there, we are calculating back. So whatever voltage he is getting, he is calculating back what should be the pH. The instrument itself is doing a simple calculation. So here in mass spectroscopy, from the instrument, it is getting the mass by charge ratio, and then we are getting the weight or the mass of a mass by charge ratio. We are getting the mass of the individual fragments. Okay, so most of the instrument, that analytical instrument that used for analysis, UV spectroscopy, fluorescence, they are all doing something like that. What they are measuring is then calculated back. They will be transforming the data into a more suitable for us to understand. Okay, so application, okay, there are so many applications: molecular weight determination, structural characterization, gas phase reactivity study, qualitative and quantitative analysis of components in a mixture. Okay, so these are just few, but if you go individually, these are quite huge. That means it will become a very huge application. Okay, in any of the, wherever we are looking at, we are doing a study on any component, we are dealing with any molecular component or anything that can be utilized to have a mass spectroscopy to give an authentic information. Okay, and it can be coupled with GC, it can be coupled with LC. Okay, it can be coupled with GC was not that challenging, because mass spectroscopy, by default, it requires samples to be in gaseous form, and mass spectroscopy is worked in a very high electrical and magnetic field. So any sort of solvent or other things cannot be inside that instrument. It will spoil the instrument. Okay, the mass spectra, the environment is, it can only accommodate gaseous phase. It cannot accommodate any liquid phase. Okay, so because it has a very high electrical and magnetic field in that mass detector inside, and then use a very high vacuum to remove the other things that is not required. It is very, very important. Later on, we'll see why it is so important to have a very high vacuum. That's why the solvent type of things, the liquid things, is prohibited. Okay, so GCMS has been appeared long time ago compared to LCMS, because people were not thinking about LC to use with a mass detector. LC was going with UV, fluorescence, electrochemical, all sort of this. But that's why a lot of questions in my last lecture, I discussed that GC can answer you only 20% of the molecule separated, others cannot. So it was a frustration, or it was a very big challenge for the scientists to couple the LC with the mass. Okay, so from LC to connect with the mass, the bigger challenge is to how to get the interface to remove the solvent efficiently, so that you can just only get the sample in gaseous phase. So the struggle take more than 20 to 30 years to have so many interfaces and so many failures and other things. And in current last maybe 10-15 years, LC become very useful tool, especially for your lecturers, those are involved in natural products. I think they are very happy to get LC, especially LC to be coupled with MS. And this was a very huge good news for those are working with natural products, especially because they were been in not having the opportunity to use the MS using the GC, because GC has only limited. Because you know, in natural products we have the huge number of molecules and compounds have different characteristics. So some of them can be answered by GC, but most of them can be answered by liquid chromatography, because liquid chromatography is very what do you call, a suitable environment required. That means ambient temperature or room temperature. So, and then it doesn't challenge the stability of the compound. Okay, because for GC you are challenging, because you have to send it in a gaseous phase, you have to use high temperature. So you are challenging the stability of the compound. Okay, so once the LC has a good interface and then mass getting consistent, because previously when the LCMS started, due to the interface changes, the consistency and reproducibility was not there, which is very, very important when you are doing such structural elucidation, quantification, qualitative analysis, because you want to confirm this one is the same thing you are getting every time, every time, anywhere in the world. Okay, I am not talking about moon, inside the world, is it? Okay, so when you have this thing, LC, especially last 20 years, has become a very established LCMS system, because the problems of changing from liquid to gas, the interface has become very, very successful. And then now we are frequently referring to LCMS. Less people are going for GCMS, because the application is very small, and then LCMS become more popular because we can handle more of the what do you call, samples. Okay, so that was a little bit of that one. So the basic of the mass spectra is that this is the mass spectroscopy's basic principle. This is the very basic principle. You will see a very complicated things later on, but all these complicated things has been established on this what do you call, very simple equation I have shown here. Okay, just like if a building, if you're talking about a building, the building is huge, but it started with a very small brick or a very small concrete. That's the unit block. Okay, but the building is become very complicated design, but you are using those units to be. So whenever you see very complicated things, don't worry, don't scare. Even sometimes we get scared, we are so long here, but if you can go back to the origin, you go back to your basic, then you start to build your thinking that on that basis, then you will see the things become easier, because everything has to follow a particular rule. Okay, so particular rule has to follow, otherwise the world will become like chaos, is it? Otherwise you see the sun is going one way, moon is going one way. No, they are following a particular system. So when we talk about nature, nature is following a particular system, and then when we're doing something with that, this also has to follow a particular system. Otherwise, if not following particular system, we cannot make it acceptable, yeah, until it is very consistent and others. So you have to follow the system. So this is the basic of mass spectroscopy. You have a molecule, you use the electron beam, okay, and then you create them in a form of ion, molecular ion, okay, and you release a electron. So this become our target. Okay, so this is the one we are looking for, because when we put this inside the MS detector, he will detect this one. He will not detect this one, he will not detect this one. Okay, so MS detector is meant to do this type of detection, and it can do a very specific type of detection. Okay, so if all of all the student of your biomedical science come to our UIA campus, okay, so we will not be identify you individually, isn't it? Okay, but if Dr. Ikhwan come together with you, so he will be the one who can identify you individually. Okay, so mass detector will be identifying these things only. They will not identify this and this. So we'll get a very specific result. Okay, the specific output based on the molecular ion. Okay, very interesting thing. I think, do you know what is this? Anybody? You play these things? What do you call this one?
Puzzle.
Huh? This is called?
Puzzle.
Huh?
Puzzle.
Jigsaw puzzle, is it? You see, this is a jigsaw puzzle. Okay, so this picture has been cut into pieces. Okay, all the pieces are haphazard. So this is jigsaw puzzle become very challenging when your number of pieces is very high. Is it? So I think a lot of students, even the lot of old people, the adult also, they like to do this jigsaw puzzle because this is a very good mind game. A very good thing. So mass spectroscopy is something like jigsaw puzzle. You have a molecule. What we do, we cut it into pieces. Okay, we cut it into pieces and then we put them together again to create this one. So we have the jigsaw puzzle, that means we have the molecule, we cut them into pieces. Okay, this is we desperately cut it. Okay, because we cannot handle the whole molecule alone. We have to handle individually. It's become easier for us. We can see it properly. Okay, we take this one and you see, okay, what is this? What color is this side? So which color it will match? Okay, then by that way we try to put them into here. Okay, we start to arrange and then sometimes we see, okay, almost similar, then we change it again. The ultimately once we reach here, that means this and these are the same. Is it? So when you match this one and this one, then only you say, okay, my puzzle is complete. So in the competition, you will get a success. Okay, so same thing we are doing in MS spectroscopy. Okay, we're taking a molecule, we cut it into pieces, we call them fragments. Is it fragments? This individual of these pieces of molecule, we call them fragments, and then we are ionizing them. Okay, and then identifying them, and then once we get these things, and then we are trying to put them back individually. Okay, okay, see here, none of the pieces is left. Okay, there is no more pieces is left, all the pieces has been taken care of. So when we utilize all these fragments together and we get back the structure, then we say, okay, we have done a good job. Okay, so mass spectroscopy is something like this jigsaw puzzle. Okay, is it clear? But my humble request, please don't write these things in your exam question answers script. This is just for your understanding. Okay, so please, just to give you a clear picture that what we are going through, because I know mass spectroscopy from the name also, a lot of lecturers also very scared, especially when we have the lecturers from medicine background or biomedical science background. They also get very confused when we talk about mass spectroscopy, NMR, all this spectroscopy. But I also don't want the students to get scared because you're not having chemistry background. So trying to make it a very good, comparison, so that you can visualize. When you start visualizing in your space, in your thinking, then only you will be able to understand. Okay, so you see, this is a methane. This is a methane, is it? CH4, is it? CH4 methane, and we put the electron and then it becomes a positive charge methane. This is what we call molecular ion. Okay, molecular ion, that means it is having the weight of the molecule. Okay, but it is in a ionic form now. Okay, so once this molecule is in ionic form, we call it as the molecular ion. Okay, so that one electron has been released from here, so we have got 2 electrons. Okay, so if we got a bit complicated molecule, ABCD plus E. Okay, because here you see all the H are same, so we're having a similar. Okay, so when you have the ABCD, E, we have the first one is this. This is the molecular ion. Is it molecular ion? Is it? This is the full, because it is A, B, C, D. If you calculate A plus B plus C plus D, you get A, B, C, D. Okay? It is carbon, hydrogen, nitrogen, sulfur. Okay, so you have to add in the molecular weight of individual element. Then you get this weight, molecular weight. Then we get this molecular ion. Okay, so this is the molecular ion that is exactly the same with this main original molecule. So we have to have this one present. Okay, and then after that you see how many combination you can get. Is it? So many combination we can get. Yeah, because you, just like you want to cut a piece of what do you call wood, or a piece of what do you call anything, the bread or whatever, and then somebody blindfold you. Is it? Blindfold means you cannot see. Then what do? You just chop. You don't care where you are chopping. Okay, so electron, when we are putting the electron, we call it electron bombardment. When somebody is bombing, unless he's a sniper or sharpshooter, he cannot, when you are shooting something, you cannot be very, very accurate. Is it? So when you are doing a continuous bombardment or the continuous shooting, that means at that time you cannot be very, very accurate in aiming the things. So you don't know where it is getting, but it will get up with some sort of fragmentation. That means pieces. These are all pieces are called fragments. Okay, so this is just an example. Okay, this is just like we have the molecule. Okay, we had the jigsaw puzzle, the picture, and then we cut it into pieces. Okay, after that, when we pick them together, then we should have get back this one. That is the simplest way of understanding mass spectroscopy. Okay, okay, so this is another example. You see, here we give some new what do you call extra. This one, there's a molecular ion. Is it? This is a molecular ion. Then this is a 29 is one of the fragments. Is it? Then we have 15 methyl CH3 methyl group. We have 15. 12 into 3, 12 plus 3 is 15. Okay, so you see this one is detected, this one is not detected, is a radical. Methyl radical is not detected. Only the positive cations will be detected. These will be detected. Okay, so the what do you call this is become 3 different fragments. We have 3 different fragments. This is what we have for this particular the what do you call alkane. Okay, so okay, molecular ion is usually the highest mass in the spectrum. Yeah, that is represent to this. It cannot be more than that. Is it possible to get a higher molecular weight of than this one? Is it possible? It is logical. No, because you started with 30, you cannot get 32, 33. But later on we'll see why we'll get. Sometimes we get. Okay, we'll see why. But it is technically it is not possible to have this more than the molecular weight. So molecular ion peak will be the ratio, the one will be the highest, and others will be smaller than this, the molecular MZ ratio or the molecular mass. Okay, the fragments. Okay, just now we are talking about that if you can get more than that or not. How many of you know about this word, isotopes? What is isotopes? Anybody?
Students, please answer.
It's okay, it's okay, it's okay, no problem, no problem. Okay, even sometimes I also don't chance to get into suddenly somebody. Okay, okay. So isotopes, I think everybody know about isotopes. That actually when we have that we know hydrogen weight is 1, is it? Atomic mass is 1. But in the nature we have some hydrogen, we have the atomic mass is 2, but very rare, very small amount. Okay, we call it deuterium, is it? Or when you have H2O, we call it water. When you have D2O, we call it heavy water. Is it? Because it is heavier than the normal water. But you see the percentage is very, very little. Is it? Very small amount. Okay. So same for all this carbon, nitrogen, oxygen, fluorine, silicon, phosphorus, sulfur, chlorine, bromine, especially the iodine group. And bromine, you see, 81% got B4. Is it? 79 and 81. Is it? So that 81 is 97%. Is it? That is almost like same 100% and 97%. That equal number of, you have a bromine, you will be having a bromine of 79 atomic weight and 81 atomic weight, almost the same. Is it? So that's why isotopes for the mass spectra, for those containing the what do you call aldehydes, sorry, aldehydes group, halogens groups, they will be have to carefully determine. So now we know that in the previous slide, what we have said, that molecular mass, molecular ion peak is with the highest number. Okay, but now we know because of this isotope, sometimes you have a higher what do you call mass by charge ratio, or the fragment with having a higher weight than the the molecules, then it is possible. Okay, now before that we say it is not possible. That's now they say it is not logic. We start with a 30 milligram, 30 what do you call the molecular weight. How I can get to 32? But now I know, because if I have these are these elements inside that molecule, then I should not be worried, or I should not be surprised. Okay, because this is the rule of nature. There will be isotopes. Isotopes is in nature, so we cannot control it. It will be there. Okay, so that's why when we have some molecular the mass and charge ratio, molecular ion peak, we get some of them is higher than the molecule's weight, then we should look into the issues of isotopes. Okay, that is the key point. That's why I say that mass spectroscopy, when you try to see, look at those structure, those radicals going here from there, don't get confused. They all follow very simple rules. If you have the rules always together with you, it is very easy to do the puzzle complete. Is it? At the beginning we said we have a jigsaw puzzle in mass spectra, so we can all these small rules and regulation, because they will follow it properly. Okay, so you see, so this is an example of the mass spectra, that the average water, is it, water was supposed to have what, 18, is it? But you see, if you take an actual, so we have the average weight of this one is the, when you got the one, but when you took it as a monoisotopic mass, okay, but you can have different. You see, the average weight when take is, the mass we get is 1156.6, but we can have these fractions as well. Is it based on the isotopic requirement? So you see, in mass spectroscopy we can get this specific peak and also these peaks that will show you that how accurately we can do the resolution. We can separate them. You have 55.6, 56.6. These are very small amount, small changes, but a very significant differences is what we call represented in the mass spectra. Okay. Okay. So MS system. System is the one that when we took all together. So sample reduction system, this sample reduction system, mostly before that will be our LC or GC, our chromatographic separation, then it will come into the mass spectra. Okay, so we are getting the separated things, and then the mass system will start working. Okay, and then mass sample interface, that means if you have the GC, no issues, you can enter. If you have the LC, you have issues. What is the issues? Your issues is the solvent. Okay, so if GC, you can directly couple, no problem, because GC is gas phase, so mass spectra always welcome gas. Okay, but mass spectra cannot welcome liquid because it is having a very high electrical and magnetic field. So if you have any sort of solvent, that will create a very big chaos inside. Okay, so that's why when you have the LC liquid chromatography samples coming with liquids, then you have an issue. You have to have an interface. You have to remove that solvent part. Then only the dried things or the gaseous things will enter to the system, and you have the ion source and analyzer and detector. Okay, and vacuum system continuously there to make the system clean from the unwanted things, which will be the term we'll see. Okay, are you scared looking at this picture? This diagram? There's nothing to worry about. This is how it looks like a schematic of a mass spectra inside. Okay, we just check like a cross-sectional view. Huh? Just like if you show me the cross-sectional view of heart, I will be scared. I will say, oh, what's going on? But for me, for the doctors, it's not an issue. For biomedicals, they are always looking underneath. They say, because when I go as an examiner, or those, what do you call, when I see the presentation of biomedical science, when they talk about the what do you call, histology section, all looks same to me actually. But for those experts, they can say, okay, this is a cancer sample and this is a healthy sample. For me, all looks like red. But for the expert eye, they can say, okay, yeah, I can see the difference. For me, it looks like, oh, they're saying the same slide every time. You see, 10 of this. Okay, so they look so alike. So don't worry, because this is based on the experience. Okay, so just now we are talking about the mass system. So the sample. Okay, the sample will be introduced. Before that will be your LC or GC. Okay, so when the sample start entering, we say it has to be in a gaseous form. Okay, so we'll be having electron beam. We have a chamber where we'll be having electron beam, or we can also tell that electron gun. Okay, electron gun means what? It will be shooting electron towards the molecule. So we have the nice picture, just like in this, just like we saw the jigsaw puzzle just now. We have the nice picture entering the system, and then you cut it into pieces. Yeah, so the electron beam will cut it into different fragments. Okay, so and then they will be guided with this negatively charged. So what we want, we are positively charged. So they will be attracted by this negative charge plate towards this pathway. Okay, so the neutral molecules will be removed from the vacuum. Okay, so the pathway will be attracting them and guiding them. They are just like guides. Say if I go to University of Sumatra Utara, I need Dr. Ikhwan to bring me around because I don't know where is the building, where is the lab. If I go to, but if he come to UIA, then Dr. Alfie or me, I have to guide him. Okay, so this is same here. Just think, always compare. So the environment here is guiding the positive cations only to enter into the system. Okay, others are all getting out from the system. The vacuum is cleaning it up. All the free radicals, negative charge, everything will be go out. Okay, so they will be focusing inside the magnetic area where there will be very powerful magnetic field. Okay, so you have a very powerful magnetic field. Okay, so once you enter this positively charged cations or the ions, the fragments, okay, they will now be deflected. Is it? Okay, I give you an example that you, especially when we have this small time, we have this school time, we have small magnets, and we play with the magnets. Is it? We try to connect them with everything. Whatever we see, we want to collect anything metal, we go and try to play with it, and then the needles, pin, all these things. So small things we can play around. But if it is like a big, just like you have a, what do you call, the stainless steel, the steel, what do you call, cabinet. So your the small magnet will go and attract and attach to it. The things will not come to you, the magnet, is it? The magnet will go and attach to the thing. So that means the based on the mass, okay, the magnetic field is strong. How the magnetic field? So the molecule, the fragments, they will having, because they are having different molecular weight. okay, or the fragments weight. So they will having a deflection in this magnetic field differently. Okay, that will be the key. That will be the key to isolate them. Okay, before that in chromatography we say that we are making the stationary phase and mobile phase different to separate them. Here we are using the magnetic field and we cut them into pieces. Now they become small piece, so different pieces will be having different weight. Okay, and then we are entering them in a magnetic field, so different pieces will be behaving differently. Just like if you think about a very windy day and you are in near the what do you call the pantai, yeah? Near the beach, you see that the things, everything is like blowing up, huh? Just like small things, those are small things, they are blowing up, but human being, still you can survive. But in some cases if become a cyclone, huh? Then the human being also blown up. Even big ships can blown up from the sea to the so this is what I am trying to make you understand, that when you have this magnetic field, they will behave differently and they will come to this area, the collector area, not all of them at a time. They will come at a different time. Okay, how they are coming at a different time? Because they have been deflected in different way, and it was found that the small thing, just like I said just now, if it's very windy, if you go near to the beach, you will see this piece of paper, the small plastic with the what do you call, glass bottles, everything is moving, but you still can survive, you can stand still. Is it because you are heavy? Is it? So the small things and the big things, they will behave differently. So small things will be having more deflection compared to the heavy, and then they will reach faster to the collector. Huh? But this delay is not like after 1 hour. No, they will be delayed in millisecond or microseconds. Is it? But even that thing can be registered in this collector or the detector efficiently, and everybody will come according to the time. Okay, and everybody will be registered according to their molecular weight or M by Z ratio. Okay, so this is what we call the ionization stage, and this is the mass analysis. When we are separating the masses, we are making them into pieces. That is the fragmentation phase, the stages where we are doing the ionization, and then we are doing the analysis of mass, and extra all things has been removed from the system. So this is a general schematic diagram of a mass spectra. Okay, this is the earliest mass spectra. Later on, we have to do some changes here and changes there. Let me see how are the changes. Okay, so first is the ionization. That means the fragmentation. We have to do ionization. There are several types of ionization available. For gas phase, GC, we have electron ionization and chemical ionization. And for liquid phase, we have API, atmospheric pressure ionization, and APCI, atmospheric pressure chemical ionization. And also we had atmospheric pressure photoionization. And then we have solid. This one was the latest development. Okay, we have a solid material, we can mix it with some sort of binders, and then we can use this MALDI, matrix assisted laser desorption irradiation. Okay, so MALDI, then this also now a solid samples also can be utilized to have a mass spectra using this MALDI, especially for big polymer samples and others. Okay, so this is the sample interaction phase. And then in terms of polarity, GCMS, this is mostly non-polar substances, EI and CI, electronic ionization, chemical ionization, and ionic, because LC consider mostly ionic because we have different types of solvent. Okay, don't always remember LC-GC. The major difference is the mobile phase. Okay, mobile phase play a very important role in LC for separation. Okay, so that's why we have more ionic and things in there, and mostly in GC we'll be having non-polar and non-ionic things. Okay, so molecular weight wise, we can go very high molecular weight in LC. Okay, in GC we cannot go more than 10 to the power 2. Okay. Okay, this is the earliest, okay, electron ionization, most widely used. Okay, high energy electron is supplied when the samples coming in, nitrogen, sample solution in nitrogen gas. Okay, then high energy electric field will create the what do you call these charges. Okay, that is we call them electroionization. Okay, so 70 electron volt. Okay, this is the general. We can go lower than that, we can go bigger than that. Okay, now I say if you want to because if you have say small a cutting set of knives, is it? So when you have the cutting set knives, you see there are very raw type and there are very fine type, is it? So when you want to do raw cutting, that you want to put the big pieces, you use one particular type of knife, is it? But when you are trying to peel them and then make some shapes, then you use the crafting type of knife, is it? I had the picture, but I forgot to put it there. So anyway, so I will show you, but just think about it. So that when you have you have to want to do a very nice design or peeling, you use a crafting knife that is very small but very sharp, and then you can do it precisely, because you see that a lot of design can be, they are doing a very nice design on tembikai that become like a flower, something like that. So they need a very small knife. But if for me, I use a very big one and then chop into pieces, and then for me, tembika, I just need to take it, is it? Cut and bake. But for those at decoration, they do a very nice. So here also, when we have this minimum, this electron volt, we will be having a nice fragmentation. Lower than that, maybe having fragmentation, but you will not get a detailed picture. And higher than that will be many. Too much fragmentation, you will get lost. So mostly at this 70 electron volt fragmentation, this is the most oldest technique, electron ionization, that electronic bombardment, just electronic high energy electrons will create the ions from the gaseous phase. Okay, so this is what we call the electroionization technique. This is the ionization, that means we are creating the molecular ions or fragments into ion. Okay, chemical ionization, this is a bit tricky. Here, what we are doing a chemical ionization. We are not, of course, we are using electronic energy, but we are using here the electronic energy. Also, we are making the gas phase, a particular gas into ions. Just now we show the methane, we make it into ion. So we make a gas phase into ion. Okay, the purple color. Okay, and this one is coming from the samples coming, neutral samples coming. Once they are interacting with these gas phase ion, this gas phase ion will change them into positive ion, the samples. You see, they become red. The ash color become red. The purple color become no charge. Okay, they will become they become blue color. They give their positive charge to this one, the sample become positive, and then they become neutral. They are going out from the system. So you see, very nicely changed that the things are getting charged using the what do you call, the gas phase. So this is a chemical. That's why it's called chemical. We are not using electrical energy. Before that, we are using electrical energy, because you know that if you have an electron, just like when you go to the atom, atomic electronic configuration of an atom, so you see the outer electrons are very, that means that can be used for most of the reaction. It can be loosed or you can add in. Okay, but in certain cases, just like you have the halogen group, they have 7 electrons. They need 1 electron badly, is it, to fill their octet, is it? So if you get a hydrogen, immediately they will combine. That's why you see the hydrogen acids, all the acids, they are very reactive. They are very reactive because hydrogen available, and then so when you have the chlorine and hydrogen, these are called ionic bond. So they become, so hydrogen is very eager to give up 1 electron, and chlorine is very eager to take 1 electron. Okay, so they are very reactive to each other. Okay, so this is what happened, that when you have this type of scenarios, we can actually, this is what we call that when you are using the electrical energy, you are removing 1 electron, 1 electron from the molecule, so it becomes positively charged. So this electron become very highly reactive. This molecular charge electron will become highly reactive. This is what we call that when we remove 1 electron, we call it ionization energy. When you remove the first ionization energy, when you remove another electron, is second ionization energy, third, fourth, you can go, but the more the ionization energy, you are going more towards the center of the atom, it will become more and more energy required. Okay, so the first ionization energy always will be the lowest. Okay, so here we are using the chemically charged, okay, the charged gases to make the molecules positively charged and then entering to the system. This is what we call the chemical ionization. Okay, so we can see how it looks like in a pragmatic force. Okay, the coronal discharge. So the charged gases. Okay, sample is coming and then sample become positively charged. Okay, and heat should be there. And this is the interesting spray ionization. Electron will be sprayed the ionization. So when from the LC the samples coming out, they are coming like a nebulizer. Huh? Have you had the idea of nebulizer, how nebulizer is working? A very liquid things, when you spray them in a very fine droplets, that is called nebulizing, is it? So when have a hand spray, just like we have a hand spray for cleaning the things or whatever. So you see that the knob in the mouth, if you change tighten it or you loosen it, then you see the spray, they are coming like more like a flow, and when you tighten it too much, then it becomes like a mist. This is what we call nebulize. Is it when the droplets become like a mist, just like when you press the aerosol, is it the mosquito spray or deodorant, all these things, you see this is the, you see the liquid, but it's come out as a mist, so that easily it can be spread. Okay, and then the easily can get evaporated. Okay, so this is what is the job of nebulizer, to throw the sample, liquid sample, in the sort of mist. So they become very small things, so easy to get evaporated. The solvent will be get evaporated. Okay, so the evaporation will cause them to get rid of the solvent. So when they have evaporation, and then they will get the electrical charge to get them charged. Okay, and there will be into small fragments, is it? They will be charged at the big original droplet, they already charged. Then when they're coming into the mist, they're getting the evaporation, and then they become smaller parts, is it? In here I show you a more enlarged picture, and then they are entering into the mass detector. Okay, so this is the interface area, okay, where we are creating the ionization charge. Okay, this is how it looks like in a LC interface. I see this guy is cleaning, because you see, so a lot of this salt has been deposited, and this is the place where the things goes in. Okay, so this is the connecting to the, and then you see all these things has been deposited. So once a while you have to really clean this part of the regularly. Okay, this ionization chamber. Okay, this is how it looks like. Okay. So this is what do you call it is the graphical representation, that how it works. Okay, the samples are ionized and in solution, nebulized flow using from the ESI probe, stainless steel capillary, very fine capillary, just like our hair, and then ion evaporation, and then the ion will be entering to the, when it get evaporated, they will be entering to the system, mass system. Okay, CC is also atmospheric pressure chemical ionization. Okay, so there will be a PCI. This is we call from LC to coming into the evaporation stage, and the reagent gas will transfer the charges. Okay, so the difference between the just now the ESI and APCI is that this one will come from the directly from the system, and then the evaporation will take first. Okay, because there the evaporation takes later, is it? But here evaporation will take place first, and then the charge, what do you call, the gas will react with the, because in the ESI just now, the evaporation stage was the later, okay? But here, evaporation has to take first, charge first, and then we have the charge, what do you call, gases, and then we can transfer the charges to the molecules, the yellow one, the fragments, okay, analyte, okay, and then it will go to the mass detector, okay, and then we have photon, photon, is it? So photon means UV. Yeah? So this has to be come, because in terms here you will be having a UV light once the things is coming, so that will cause the ionization. Just now we are using the electronic state, but here we are using the photoirradiation. Photoirradiation, that means UV light to get the ionization and then the transfer to the system. Okay, so the heat, the UV lamp will be changed. There's just exactly the same, but instead of here, the UV lamp will be used for the photoionization. Okay. So then MALDI, okay, matrix assisted laser desorption ionization, MALDI, what you call it, MALDI. Okay, this is mainly for the solid matrix. This is how it looks like. You have the solid, you have the laser beam. Okay, once you have the laser beam, so this will extract some of the part of the samples. Okay, so the samples will get ionized using the laser charges. Okay, cyanohydroxycinnamic cinnamic acid. Okay, this is the platform used, and then this is the first time it has been used for the solid samples. It has been mixed up with some binders, and then it will be, some of them will be excited using the laser beam, and then this will be charged according to that laser. Laser is very powerful. Okay, so that can use the ionization energy. So this will create the ionization energy. The analyte will be changed into molecular ions, or fragments will be changed into positive ion. Okay, so this is that UV laser. You see, nowadays laser is being used in a lot of things, because especially even for the eye operation nowadays they are using laser. Even in some side of internal organ, the one they are using laser, because laser can cause a less bleeding. In some cases, some extraordinary what do you call, high specs or sophisticated operations also they are using laser, because that causes a small less bleeding. And some of the part, they also, the bleeding part, they also use the laser to just stop the bleeding inside internal organ while they are doing a surgery. Okay, so laser has a lot of use, but those are very mild laser. But this are, we are talking about a high energy laser, whereas we'll be using the laser to what do you call, to excite the analyte into ions. Okay, so we are talking about the ionization. Now we talk about the analyzer. How the things get analyzed. That means the mass has been arranged, or the mass are analyzed. Okay, there are few types of analyzing. So there are single quadrupole, there are triple quadrupole, there are ion trap, time of flight. I think natural product chemists are very, very obsessed about this TOF. But I'm not very obsessed about it. I'm most obsessed about triple quadrupole. Okay, because I'm an analytical person, so I go for analysis. So later on we'll see how. But anyway, no, because these are all complementary. So now, okay, now this is the very interesting part, that how you are going to separate them, the mass. Okay, so once we have that, now we have done the part that we have got our separation done by LC or GC. Is it? They have done a very good job. So they separate the ions and molecules. So then they send it to us. Then what we do a little bit of ionization. That means we cut it into pieces, we make it in the different fragments, and then we put them positively charged, which is very, very suitable for a mass detector to analyze the mass. So now what will happen once the things will be inside the mass? So can you see these four rods? Is it these four rods? There's a quadrupole, four, the quadro. That's why you have the quadrupole, and you see they're having positive, negative, positive, negative. Okay, so they are oppositing each other. So if you remember, as just now we are talking about the small magnet during the school time we used to play. So if you have two magnets and you have a one small pin at the in between them, so you will see if the one is nearer, it will go and attract that particular magnet. But if you have them in the very, you can bring the two magnets very close to this one, then at the moment you will see that the pin becomes stable. It's not moving. That means what? The attraction force for these two magnets become same. So it is standing at the middle. Am I getting clear, or is very complicated? Just imagine that you are playing around with two small piece of magnet, and you are having a small piece of pin or anything, that means or the gems clip or whatever on a piece of paper on the floor, and then you are trying to approach that pin from both sides. So at the stage come, you will see that if you can balance the differences of the one, and then you have a very equal shaped or equal strength magnet, then you will see that the pin is standing holding at the middle. It's not going to the left or then not going to the right, or it's not going to attract any of the metals, the magnets. Okay, so it will be in the middle. Okay, so and then if you can think about that how the balance of our universe, the moon, the earth, the sun, these are all actually balanced by electromagnetic force. Okay, the force are so that they will be standing at a particular space and they will never change. If there is any change in the electromagnetic force or the balance of this one, then that day will be the harikiyama. Is it? There will be no attraction, nobody will follow the rules. Okay, so exactly the same thing is happening here. When the molecule or the fragment with charge is entering to this area will be having a high magnetic work, and then this positively and negatively charged ion, they will guide it in the middle pathway. This will not go to the any of the electrode. Okay, so they will be so equally that if because it's a positive ion, it should go to the negative electrode, but you have a positive electrode here, so they will repel each other, and then ultimately that is arranged in a so nice way, the quadrupole. Later on we'll show some picture of that quadrupole, but this is the but if you open usually they don't allow you to open, this is only in the manufacturer side, the instrument, but it is so nicely arranged and so accurately and precisely arranged, so they will be having a similar potential, so that this molecule, the molecular fragment that is entering the system, they will not be attracted to any one of them, and they will be guided throughout, and they will be also guided in terms of a oscillating pathway. And at a time one will be going, but if you have more, they will be also able to guide them accordingly, but at a time one they will take care. So ultimately this will be guided towards the detector. So this is the guiding part. So this is what we call the quadrupole, single quadrupole. You see, this is the belt going on, and only the blue color things are going into the detector, others are not going there. Okay, so this is the one which is guiding the system. This is what a single quadrupole. Okay, and this is the triple quadrupole, Q1 Q2 Q3, sorry, Q1 Q2 Q3. Okay, so Q1 is the first one, MZ, precursor ion, filter specific precursor ion. Okay, use as collision cell. This is the beauty of Q1, Q2, Q3. They have the triple quadrupole, Q3, triple quadrupole. So once you have fragmentation here, you identify one of them and break it again. Okay, so this is what we call the collision cell. We break it again into another part of fragments. Okay, and then we analyze that part only in Q3. Okay, so we have say 5 or 6 fragments here. We identify one of them, and then we further cut it into pieces. We make it fragments. Okay, so and then we identify what are the pieces we got. So what will happening that when you have the Q3, okay, when you have the Q3, Q, that means triple quadrupole. Okay, so what is the best thing about it, that if you have a combination that is very closely related mass and other things, and you are having problem with the single quadrupole to analyze, then what you can do for the confirmation, you can identify or you can extract any of them, any one of the fragments, and then you bombard it again in the collision cell, okay, and then you cut it into pieces again into make fragments, and then you get only for that particular fragment you get another fragment. So you are getting a confirmation of this fragment from here, and then individually you can choose any one of them, and individually you can check them separately. Okay, so just like you go for examination, is it your exam, you have examination, that one you go written, that all of you go written and you answer the same answer script for say 10 or 20 students, you answer from the same question paper, is it? All exam questions are the same. Okay, so your supervisor get the answer script back, and then he is not very happy, he want to find out who is the best among you. So now he says, okay, I am asking for a viva, for a face-to-face viva. So when he asks for a viva, then he go for one by one, is it? And one by one, and he evaluate you. Okay, so you give exam. Okay, this is a exam, that one written exam. All of you got the same exam question, same time everybody, but you all of you have done very well. Your supervisor, Dr. Ikhwan, is having difficulties that who is the best. I am very difficult. I don't know. Everybody has answered. They have answered very well. Everybody got 10 out of 10. Okay. So now he says, okay, I have to do something more. I have to get you that who is the first, who is the best, and who is the lowest. So I go for a face-to-face viva. So now he go one by one, and now he asks you question separately. Okay. So you go one by one, and then he says, okay, now I know who is first, who is second, who is second. He can make the differences because you come one way. So same thing here. We have all the fragments here. So if this is not, you are not happy with this fragmentation, you cannot get back the result done, then you can go individually fragmentation, and you can, if you get back these fragments, the parent ion. So here there was one is the molecular ion and then fragments. Here, this one of the fragments will become molecular ion for this part. Okay, so they will be having the molecular ion, and then we will be having fragments. So you will be having a double confirmation. So this type of quadrupole, triple quadrupole is very, very good for what you call quantification. Okay, that's why we have the single ion monitoring. We can say that single ion monitoring, this is what we are having here. Single ion, we can monitor that is fragmentation and how it behaves. This quadrupole, and this is ion trap. Okay, this is also a good type of one. So here the ion trap is something like donut shape. You see the ring? They are a bit donut shape. The sample is entering into the system. The ions are trapped inside this system, the donut shape, and then they have to have end cap. You could look at the, this is looks like a cyclotron. Cyclotron, I don't know whether you heard about it. This is cyclotron is to create energy to the charged particles. So this is like a cyclotron. This is the ions are inside here trapped, and then a very specific types of ions will be out from this cone because of the deflection from this the donut shape ring. Is it? This is the donut shape. Is it ring? They are charged, and then the ions will be trapped inside this box. Okay, all the ions, and then particular ion, the molecular ion, those are with the positive charge, will be entering into the system from the out of the system from this end cap type, because you see the shape of this one is that's why it is called an ion has been trapped, and then you extract the ion from there. A trapped ion, a number of ions inside the one, and then you extract a particular ion for this one. Okay, this is what you call ion trap. Okay. Now I think Dr. Ikhwan will like it. Time of flight. I think all the natural products chemists are very, very obsessed about this time of flight. Okay. Later on, I will show you a video of time of flight. Very interesting, very nice, actually. Okay. So this is one of the very interesting advancement in the field of mass spectroscopy. Okay. So I think I remember when I was first getting the physics class in the high school. They always says that, okay, this guy, what's his name, who created the theory of falling, Galileo or somebody, I cannot remember, that he go and in the upstairs, and then he throw a ball, he throw a feather, Okay, so different as reached in the different time. But when you make the create vacuum, they fall it at the same time. Is it because there is the attraction will be, they make it different. So this is actually what's happening in the time of flight. Okay, you see, flight. The molecule will take a flight. Okay, so these are the part we have done, the quadrupole, mass spectra, then ion guide, the molecule will enter here. Then suddenly you give it a push. The molecular ions, all of them, you make a push to all of them. Okay, but you give a same push. You don't give one high, one low. No, same type of energy has been given to all these molecular the fragments, and they will go to a very tunnel type. The shape of the top, those the GCMS or LCMS coming with the TOF time of flight, they will be having a cone at the top. So that is the area where this flight will take. That is that it will be getting a pass. That means you are throwing. Let's say I am throwing a stone. Okay, if the stone is smaller, it will go high. Is it? But if it's small, bigger, it will go not very high. But it will take longer time. So here also the smaller things will be coming back faster. Okay, so the difference in the flight, is it? The difference in the flight that will make the changes in the reaching to the system. So different fragments will reach at this area, that is the collector area or the detector area, at different time. So usually when the is not detector reflection mode, this is a reflection on and off. On wise there's no flight, but off, this is when it is on, then there will be reflecting into the reflector and then coming back to the reflector mode. That means it is coming back to the detector. Sorry. Okay.
Dr. Hilal, I have a question.
Yes, please.
What makes the difference between these ions to reach the detector? So what determine the difference for the time of flight?
Okay, in the time of flight, it was found that the smaller they will go high and they will come back faster. Smaller fragments.
Or the smaller fragment,
yes,
they will
go high.
They will fly faster.
Yes. Okay. And same like the one we have seen in the magnetic field. At the beginning, I show you the magnetic field that has been the smaller one deflecting more. Is it? Here also a similar concept. Okay. But this one is very good for scanning. When you have the qualitative, that means say natural products, you have a lot of unknown products. So this will give you a very good result, because the scanning types of things, that when you get how many you can get. But quadrupole, triple quadrupole is more on quantitative, is it? This one more on qualitative. So when you have to do the quantitative, you isolate the ion, then it's better to use triple quad. It means 3 quadrupole. But time of flight, you can do quantification, because if you just send one sample, it will give one flight, is it? But it is a loss for you, because this one is meant to do the scanning, is it? To do how many, that is the scanning will be just like we have the UV. You see they have fixed length, fixed wavelength, variable wavelength, and we have the PDA, photodiode array. This is also an array. The detector is like an array, is it? There will be a lot of samples. The things can be detected at the same time. Okay, so later on we'll see how it looks like. Okay. This is another representation. So some of the top, we don't have the quadrupole. Some of the top is only top, is it? So once there's the ionized, there is no Q. Okay, that's why you will see there is LCMS top and LCMS Q top. Okay, Q top means they have one quadrupole. Another level of separation is done here. Okay, so the Q top is more expensive than normal top, is it? But the time is the thing is saying you have the getting a separation here, then you get a better separation here, is it? But it is expensive. The only thing that is expensive, because you have a quadrupole, single quadrupole, and a top. Okay, so this is your choice. You can buy only top. Okay, it's okay. Okay, no problem. This is up to, that's what we say. This is a customer's requirement and what you want and what your research want. Okay, but for a research laboratory, QTOF is the most suitable one, because you get the ultimate all separation done nicely. Because if you have just a TOF, maybe you will get jumbled up. You are not happy with the separation. Yeah, I will have it. So Dr. Ikhwan, make a budget for QTOF. Don't buy it.
Yeah, the
When you
QTOF.
put the budget, put for QTOF, the expensive one. Because that is QTOF is
Oi.
very good, very good actually, especially for natural
Very
product
good one.
chemistry. When you are all those
Mm.
metabolomic, that means that when you are talking about the biological samples like human or your animal samples, all these things, this QTOF will be very, very good for scanning, for identifying the molecules
Yeah.
inside the one. There's the metabolites. All these things is very good. Okay.
Now I understand why Dr. Alfie always asks QTOF.
Now you understand actually what is the. So,
Yeah, now I understand.
Okay, so after that, the detector is very simple. Actually, is just an electronic area that where the positive ion will be changed into negative ion, and then the electrical charges will be recorded. As I said, they will not count the ion; they will count the charge. That how many ions with how many charges. So just like we talk about pH meter, the voltage has been measured, and we say the hydrogen ion concentration. Here also like that. So it is a conical type of shape, the electron multiplier, we call it electron multiplier. Okay, so positive ion all become like electron, changes by what you call device and electron, and go into this and then reflected, so that it will further get separated from each other and then come to the detector. And this is what you call multi-channel plate reader. Okay, this is for the QTOF, multi-channel plate reader, QTOF. You have this one. You have a diode array. Array means if you look into the, I think all of you know about the diode light, is it? Photodiode light. Just like if you go to the traffic signal, I give all weird examples, is it? You look into the signal bulb. Last time, I think in the early 90s or early 80s, when we were small at that time, the traffic light has only one light inside and a piece of glass. But now you see the traffic light, they are a small light. Is it? And sometimes you see some of them are fused, so you can see a dark place in the red, or not, the full light is not red because some of them are fused already, they're converted. So this is what we call the diode bulb, is it? Small bulb, but give you a combination that looks nicer, or it can be combined, because the one, another good example is that when you have the running board, that is coming up continuously, Selamat Datang will come in front of the shop, is it? Is actually the same one, and then you are changing your diode the diode light to give the shape of a letter. Okay, so this multi-channel reader is something like that array of detection. So you can accommodate different mass at this type of channel reader, just like the photodiode array detector for UV. Okay, so UV we have wavelength, fixed wavelength. That means we can fix a particular wavelength, and we check the absorption of a particular molecule. Okay, but when we use the photodiode array, we use all the absorbance. We send all the absorbance to scan the molecule, and then the molecule will, so above all the absorbance, only one absorbance will be missing. The detector will receive all the absorbance, all the diode, only one diode will be not accepting or no response. Why? Because that has been absorbed by the molecule. Okay, that's how it works, PDA. So we get a scan. So that's why I say the time of flight with the detector is like that we can have a scan of the whole thing, which is not possible in other system. Okay, so we go back to some of the examples. In going back again for this fragmentation part, now we have understand the ionization, a little bit of that, and then we have also discuss about how we analyze that, we arrange the masses. What is the process? Like QTOF, and then we have the quadrupole, and we have the ionization, how we fragment them, bombarding, chemical ionization, electron state ionization, spread ionization. So later on came back again to the one that says 1, 2, 3, 4, 5, 6, butane. So we have this molecule, and then we have this fragmentation. we look into the numbers 72, 29, 43, 57, 15. 15 is always for methyl. Whenever you say must M by Z 15, that means always methyl. So then we have these fragments, okay, and then we look into the spectra. Okay, now we see small bars, long bars, small bars, whatever. So this is the molecular weight of the fragments. So it is having the molecular weight is 73. So we have 72. Okay, molecular ion the 72. Yeah, you have to be a positive number. So 72. Okay, so we have this is what we call the molecular ion, and the highest abundance. This is the abundance, relative abundance. The number of ions. They say this is. If we consider this one is 100. Okay, so this one will be less. That means it is how many? 18.56. That means 18 of this. Okay, so we consider the base peak. This is what we call the base peak, the highest number, the highest number of 43 molecular fragment. 43 is in the highest number. Okay, that means this is the most stable fragments. Okay, that's why we call it base peak, and this is the molecular peak. These two things has to be identified in any mass spectrum. This is the main things we have to do. That you have to find out what is the base peak, and you have to find out what is the molecular peak. And sometimes molecular peak might not be this big. It can be very small. Is it? It can be very small. In practice, this is just an example. That's why it becomes big. And why we have 73? Can anybody tell me? Because the molecular weight is 72. Why we have 73? Yes, because this is of isotope. Right? So if we, that's why I say, if we have some extra higher than the molecular peak, we have to always get back to the isotope issues. Okay, what are the isotopes present and what is this? So we have these isotope issues. We have the molecular ion more than, we have 0.5 to very small, but still it is present. So that way, see, the mass spectra will not let go anything. It will detect anything that will be having the criteria. Okay, so these are the relative abundance, and then 100% will be considered as the base peak, the highest. This is the highest, the 43 fragment. Okay, this will be the highest, and then we consider this is 100, and others will be calculated based on the percentage. Basically, this one is 100%, and these are the percentage. How much is that? Okay, okay. So what I am going to tell now is that why mass spectroscopy has become an authentic, because anywhere in the world you take this molecule, okay, you take this molecule, you do the fragmentation, you follow the exact mass spectra parameters, okay, that means the electronic charge, the flow rate, all these things is the same, you follow, you will get the same spectrum anywhere in the world. Indonesia, Sumatra, Malaysia, Thailand, anywhere we'll supposed to get the same thing. There will be no changes. That means, you see, when you're cutting into pieces, you are not blind. The instrument is not blind. It is cutting into the particular system. So the fragments are getting, your fragments are getting, they're all the similar fragments you will get everywhere for a standard particular molecule. That's why mass spectra become a very authentic tool. Okay, when you cut in a proper way. You cut in a proper way, and the stability of the fragments, the stability of the fragment shows that which one will be the most stable and which will be abundant. Okay. Okay, so this is the beauty of mass spectra, that whenever you do the fragmentation, you will get the same fragments. So the ethanol, aldehyde, you do fragmentation anywhere in the world, they will give you similar mass spectra. So the GCMS output will be the same for everywhere. If change something, that means something wrong with you. It's supposed because your instrument is wrong or your sample is something. Otherwise, it should not go out of the spec, especially when you're talking about the pure compound. I'm not talking about the unknown compound. So unknown compound, we also want to reach this level of authenticity. That's why we have the library, is it? We have the library of known compounds, thousands of them. Then it's better that we compare with the library. And nowadays it's very, just click compare, then they will give you the similarity index. Similarity index more than 80%, we consider that okay, the structure is correct. We don't go to the lab to do the structural elucidation anymore, and the life become very easy. because we created a library for authentication. After authentify the natural, especially for natural products, the compound and the environmental natural products, these people, because they are encountering new components every day. But pharmaceuticals and what you call food, we are not encountering new things every day. But natural products, those are looking for this thing, they are encountering new products. So they has to create a library, and then this library has been shared and updated regularly. It doesn't mean that this authentic structure maybe sometimes later this can be changed, whatever. So these are other issues. Okay, so that's what I'm saying, the beauty of mass spectra, that it can give you an authentic result and confirm. So these are some examples of mass spectra in extent. So you see, you cut into pieces, you got methyl 15, and then you have 29, 43, 57. So 43 is the still the base peak. And molecular ion C, you see, becomes so small, 86. 86 is the molecular MZ, the molecular ion for M hexane. And the next one is carboxylic acid. If I'm mistaken, it is an acid. So okay, so this is also 86 molecular ion. Okay, but its fragment is different. You see, this is another interesting issue. Okay, even though the both of them, just now I say N-hexane, and then this is carbonic acid, vinyl acid. So we have the same molecular mass, but the fragments are different. You see, 41, 45, 69. But just now we had different fragmentation. 15, 29, 43, 57, 71. So from this also, even though the molecular ion peak is the same, 86. Sorry. 86, is it? Molecular ion peak is the same, but even though it's small, but the fragmentation show you that they are different from each other. Is it? So that is the way it should be. That's how it gives the unique identity of particular molecule. Okay. So this is another, what you call, TIC, we call the total ion chromatography. So when you have, this is on base of time. Time, you have the ion, different ion, okay, based on time, with on the retention time, okay. And then after that, you go for this one, particular this one, and you get the fragmentation M by Z in mass spectra. Okay, this is for the total ion. That means how many ions you have. So you can go individually for all of them. All has been recorded. You just need to identify which one you want to get this fragmentation. So only that particular fragments will be entering to the mass, and you get the fragmentation. Okay, this is the mass spectra. Okay, so this is the mass spectra for 4.92. Then you have 47, 43. So this is the different mass spectra. Just now we showed. So this is the one that you can choose any one of them. Okay, so this is the total ion. That means it is the particular ion of that particular what you call molecule, and then you can fragment it in terms of by choosing them individually. Okay, then okay, halogens. Just now we talked about halogens. Okay, you see that 94, 96 bromo, methyl bromine, bromomethyl. So you see, methyl is 15 and bromine has 2, 79 and 81. So 94 and 96, 94 and 96, you see almost the same. Just now we saw the isotopes is 97%. Bromine 79 and bromine 79 is the normal one, but 81 is the isotope. They are almost the same. And that's why I say later on, we'll, this is the example I'm showing you that this give you that you have to be careful that you have two molecular peak. Is it with two different isotopes? Same goes for chlorine as well. Is it? You see 62 and 64, and you have 35 and 37. Okay, so if it is more than two chlorines, that what will happen? You have 49 and 51, and you have 84 and 88. 86 is maybe due to the isotopes. Okay, so you have chlorine 35 and chlorine 37, but the number of chlorine 37, the percentage is very low. You see, 98 is very low. Okay. So if you reduce one chlorine, the 35 will be 49 and 37 will become 58, 51. Okay, then we have ESI spectrum for trypsinogen. This is electron spray ionization. This is very good for polymer and peptides and other large molecular weight. So this gives the fragmentation, and you see the fragmentation follow a pattern. It's increasing number, the fragmentation, but from there also you can check the molecular weight from ESI. Okay, so this is the one that ESI make only the one very suitable to do a qualitative and structural elucidation of high molecular weight, very high molecular weight, especially peptides, proteins, and all these things, polymers also. Okay, this is the quadrupole, triple quadrupole, single quadrupole. Progesterone. Progesterone is a hormone, is it? Yeah, progesterone structure. We get the base peak, and then there are some other small peaks. So 315 is the molecular and the base peak. Molecular ion peak should be somewhere here. Is it? Then this is the interesting thing, that what we do, that just now we have said that okay, we have the precursor ion mass spectrum, and we choose 315, 315.1, and then we bombard it again, and we get these two fragments. Is it? See, I just choose, I didn't choose any one of them. Even 316 is there. I didn't choose 316. So this is the beauty, that you see they are overlapping each other, 315 and 316. But when we choose the mass, then they take the mass spectra, only take the 315, and then bombard it, and then get another fragmentation. So from here, I can check this fragmentation is correct, and then we can conclude that. And that's why we can do a quantification based on these fragments. Okay, so if you have a calibration, you want to do a calibration curve, this is the quadrupole, triple quadrupole will be best one to do the quantification, and also for a confirmation of the formation of this fragment, whether this fragment is authentic or not, is stable or not. Okay, so we have this daughter, we call it them a daughter ion. So this is a daughter ion for the parent ion. Parent ion is the molecular ion, this is the parent ion, and I don't know why they call it sun ion, but they call it, the fragments are called daughter ion, is it? So I don't know why they call it sun ion, is it? This is a daughter ion. Okay, so this become a parent ion now, then these are the daughter ion. So from here we confirm that this fragment is stable and it is confirmed, and then this one has been, this fragment, all the fragments will confirm the molecular ion. Okay, so this is the beauty of triple quadrupole. This is another example. If you have a bigger molecule also, you have this type of fragmentation you can do. This is the base peak. Okay, so to identify the base peak and molecular peak is very important. Is it? Is very important. This is the beauty, or this is the wisdom, or this is the expertise of the mass spectra people, the Dr. Alfie, these people, to identify the base peak, because that will make your life easier if you can identify this is the base peak. And now we are going for scan mode, for qualitative, and sim mode. Sim mode means single ion monitoring. Is it? So single ion monitoring. Scan mode is just what I said just now, that what do you call in the top, scan mode and sequence. So selected ion monitoring is very useful. Okay, so we can monitor, especially we have a lot of fragments, but more analytical side, or to check that the repeated samples. That means you have the similar samples. You want to track the what do you call, the similar molecule in different samples, whatever it is. You can choose the 3 basic fragments, 3 most stable fragments. You don't have to worry about this, so you don't have to identify, because most of the literature will guide you what are the fragments you should use. So whenever you take any component or whatever, you go and search for that particular journal or the publication, you will see they will measure, okay, 285, 315, or 100 something. With this 3 combination will be monitored, you can monitor. But this is up to you which one you want to do. But you should always refer to the published journal, because those published journal publication is accepted only. This is very authenticated and done quite nicely. Okay, so this is what we do, that scan mode. Here I think you cannot see, this is what we call the scan mode, and this is the particular ion mode just now we have done. Okay, show that one. Okay, so we are doing further. From here we got this ion, and then we get it further, the breakup of the things. Okay, selected ion monitoring. This is full mass spectra. Okay, and then we choose these 3 only. So others are not captured. Okay, others are not monitored. Here it is the full scan, and now we are selecting. Okay, we select, then they will take only the selected ion. Okay, so once we go for the comparison, okay, so there's the QTOF, let's see MSMS. This one is the most high, the targeted on recovered quantity. So QTOF with the one MS is the most expensive or the most suitable one. That means this one has the high, what do you call, features, and in terms of other things, this one will be the most suitable for those are doing research actually. But for quantification, the LC triple quad will be good enough. LC MSMS, this one LC MSMS will be good enough. LC TOF and QTOF, I think QTOF will be better because you will have another level of separation, so that can give you a one. But for the quantification purposes, just like bioanalysis or bioanalytical or the drug or metabolites analysis, I think for me, because I'm more on drugs, so I prefer this one better. But of course, this one also you can do quantification, but this one is mostly, if you do only quantification, then we are not utilizing the full capacity of this particular QTOF. Okay, this we are concluding that, of course, from our discussion, we understand that this is a very complicated thing. So as a first detector is not that easy with a 1 hour or 2 hour lecture. I think that's not good enough for you have to digest the thing. Is not, I can understand it is not that easy, and if you are not very familiar with the terms and other things, because most of the things are very new for the student. So, but don't worry, as I said, always go for the simple. So I make it quite simple. So go for the simple things, and then you start understanding the complex. So you can explore more and more and more. Will understanding will increase better and better. Right? But basic thing, that's what I try to emphasize on the fundamentals and other things more compared to the complicated, because I could show you a lot of this fragmentation of this, then you will get confused. Because when you see organic chemistry, the arrow is moving here, there, the point is going there, charge is moving here and there. This really, when it's psychological trauma, you so don't go for that first. So understand nicely the simple things first. Okay, the basic things. The basic things are not very complicated. And then slowly by reading and understanding. But now I think if you go and read other the literature or the book, I think with this little bit background, you might be able to explore more, or you will be understanding more. Because sometimes this our problem is that we cannot what we are reading, we cannot visualize. We cannot visualize that. Okay, so if you cannot understand or we cannot compare with real scenario, because when you talk about apple, so always the things that this apple should be red, is it in our mind? But when we see a green apple, nowadays they have purple apple also. I saw in the market, they have purple apple. I don't know, biotechnology has done so many things. So, but when you say apple, apple always is red in our mind, is it? So that's why they say when we talk about something, if we cannot visualize in our mind, it's very difficult for us to understand, and our mind get blocked, is it? So that's why we have to get it understand in our special, or the that it's not, it doesn't exist. Just like force, we cannot see force, but it exists, is it? So, but we have to understand actually what does it do. But we can see the impact of the force, but we cannot see what is force. It cannot be touched. But we can see that, okay, the wind is blowing, there's force. The things get crushed, that is force. You get hurt, that is a force. Okay, so simple things we can correlate, then it becomes easier for you to understand, and then it's very easy for you to digest complicated things as well. Okay, so with that, I think I will finish my lecture today, and I'm very thankful to Dr. Ikhwan and Dr. Alfi and all the professors in the meeting. I think I can see some of them. Very thankful to University of Sumatra Utara for inviting me to give a chance to share my experience with you, and then thankful to the students for being very patient and then actually very supportive, I think. Okay, so I think I finish, and then we can discuss any questions. Or maybe I think we still got some time left, Dr. Ikhwan. Yeah, Dr. Ikhwan.
Okay. Yeah. Thank you very much, Dr. Hilal. So any questions from the audience?
Yeah, you can ask about the last lectures as well. Yeah, if you have anything to regarding the last lecture, you can please discuss. Or as I say, Dr. Ikhwan, please share my email with them.
Yeah.
If they can have anything later or they don't understand, they can email me anytime. I will try to respond as soon as possible. I cannot say immediately, but
Okay.
I will try to help them anyway, inshallah, within my capacity, of course.
Yeah. Yeah. Okay. So actually, I have a question
Yes, yes,
about the ion mode. So the negative and positive mode. So should we do both of this? Because in our project with Prof. Dina, initially we received the data from the positive mode and Dr. Alfie asked for the negative one. I don't really get what is the meaning of this positive ion and negative ion.
Okay. No, actually, just now we are talking about this positive mode, is it? Positive mode, that the ion should be in a positive form, is it?
Yeah.
So now, actually, what's happening that sometimes the normal thing doesn't work for certain samples because you might not get separated them well. So if you change the whole thing in the opposite direction, then might be your interferences, because the main challenge for this type of separation is to remove the interferences or to highlight your analyte in more magnitude. That means your amplitude should be more. So if you are inside a bar, you are in a discotheque, so if somebody call you, you cannot be there and listen to them by increasing the volume. Is it? If you increase the volume of your speaker, you will still not understand because the noise is very high. Is it? You have to come out from the room, isn't it? And then when you are quiet, then only you can hear. Okay? But if you are in a classroom, okay, everybody is very quiet and you are talking, and somebody want to talk to you, even a small sound also you can hear. And if it says, okay, nobody makes sound, is it? Because it is very quiet. So, okay. Yeah. So now if you can raise voice or whatever your amplitude, then it will become very, very high. So this is what we have in the analysis, that either you have to magnify or increase the amplitude inside the samples or get rid of the, the noises. Okay. You get rid of the noises so that your concentration of your analyte will be improved. Okay. Or if it is impossible that your concentration level is very small, that trace amount, then you have to extract it, you have to isolate it from the matrix, because matrix is giving you more noises. So that's why actually sometimes we have to use something that different to see whether the matrix is interfering or not. Because most of these responses, instrument analysis, this is one of the major issues is the noise. Okay, so noise is also a signal, is it? You have to understand this. Okay, noise is also a signal. Because what is noise? Because in the classroom, when you are giving lecture, it is only you allowed to talk. It's not the student. But when your student is talking between them, that is a very important discussion they are doing. Because where to take the nasi lemak today or where to take the lunch, that is very important for them. Then your very boring metabolomics lecture, is it? So there's very good signal they are sharing. Your one is no more signal. But in the classroom, that become a noise. Is it? Your one is the signal. Yeah. You get the point? Even though that is a very, but for the not suitable in the lecture room, that where we'll take the lunch or we'll take the dinner, which nasi lemak is best. But for them, that was more interesting, is it? That is a very good signal. Your metabolomics lecture or my MS lecture is not very interesting to them anymore. Okay, so but noise is also a signal, is it? So noise is because when you are applying some electrical field, magnetic field, or radiation, whatever it is, because you want to see, you want to observe what the reaction coming in, what the response coming in, is it? That's why doctor give you the medication and then they says, okay, you come see me after 3 weeks, and then after 3 weeks you go and then they ask you to do the whole chemical analysis. That means your blood, all this diagnostic. Then he says, okay, I think I have to change the medication because I don't see any changes. Is it? So he has to do something different. Okay, but before that he has to scan you, that he didn't see any changes, so he has to. So same like here, that whenever you are having these type of thing, you have to get rid of the other things. You have to identify your analyte, that what you want. When the instrument analysis, we are applying the whole energy to everything. So whatever in the sample, it has the sample matrix, it has a reagent, it has samples, it has the impurities, all these things, they will be reacting, they will be giving response. And if your target response is lost between this noise, this is what we call the noise. So we have to always make the signal to noise ratio proper, so that you can get the amplification of your, somehow you get your analyte to be amplitude, the amplification is high, so you can identify it or detect it and separate it. Okay, so probably that is the reason he asked you to change the negative mode, because usually positive mode, sometimes it doesn't work, then you do a reverse way. So might be that will reduce the noise level. Is it? That will reduce the noise level, or it will be unique from that will be separated, that will be isolated from your matrix or the other impurities, or they will get better separated. But that one, please check with the service provider, your GC technician, or please always work together. I don't know which company you are, either Shimadju, Agilent, whatever. Always please consult with the R&D, the application team, because sometimes they can suggest you a better option, because they are always keep on all the Agilent, Shimadju, Waters, they have their research R&D laboratory everywhere in the world, and they are keep on trying all these samples in their lab, and they have all these application chemists. Never discuss with engineers. They have application engineer, application chemist. Always discuss with the application chemist. If he's an engineer, he will not give you a good suggestion. I'm telling you my experience, because engineers, they were more towards the instrument. They are not towards the sample, but the problem lies with our sample. So better always get the suggestions from an application chemist, or you can write to them, or you can in Agilent, I know you can even send sample, they will do the screening and they will give you feedback if you are using their instrument. Agilent and I think Waters also do that. So always, whenever you are doing some sort of this type of trying of the instrument, of course, Dr. Alfi is using it for lambda, maybe he give you experience. So please liaise with those application chemists from your vendor, the supplier. They can give you a better, idea, because they are always working on it, or they can let you communicate with their expert R&D team. Those are the also very high class researchers from Japan or Singapore or America. So always consult with them. But this is the basic thing. Actually, the complication, what I am explaining to you, is that always we are challenged with the sample preparation, because sample preparation is the 95% of your analysis. 5% is only the instrument. If you give a bad sample, it will give you a bad result. Your sample, just like statistics, trash in, trash out. Is it? Your sampling or data is trash, you will get a trash result. That's why the sampling protocol and all this. So same here also, when you are doing this type of sample analysis, especially the heterogeneous, like extraction or the complicated complex mixture, the sample preparation, especially to get rid of the noise, to get rid of the matrix, get rid of the other thing, is very, very challenging. And then you have to have a proper way to reduce the noise, so that only your signal will be high, it will be more detectable, as well as consistent. Because consistency is very, today, Dr. Ikwan, you got a very good result. Tomorrow, everything is gone. Hey, where is it going? This is not a good sign. That means it was not done properly. So whenever you are using this type of instrument, like CMS, QTOF, whatever it is, the consistency has to be there. That's how it has been manufactured, or it has been customized. So it should give you a consistent result. Otherwise, why you are buying a 1 million ringgit instrument? CMS is 1 million ringgit now, 1.2, I think, if I'm mistaken. Very expensive. So definitely it has been customized to give you a very high quality result. But due to your sample prep, that means your sample is not properly prepared, you might get a very lousy result. That's what I'm saying. It doesn't mean that once you just put the sample, because this is the general people's understanding that in HPLC, you just put the sample, you will get the separation. No, not that. You have to use your brain You have to pull your hair to sample preparation. A good sample preparation will give you a good analytical result. Okay, Dr. Ikhwan.
Okay.
Please,
Yeah.
you can
So
try
if
that one,
if
because maybe that is an option to get rid of the response from others, so that you can get a specific response from that one. And sometimes it depends on your molecules as well, what types of molecules you are playing around, because the polarity is one of the main issue.
Yeah. But if I just would like to, for instance, now I would like to analyze the asiatica. I have the ethanol extract of this centella. I'm expecting actually ursolic acid in there.
Okay.
But ursolic acid, yeah. But I also would like to know what other major compounds in my extract. Is it possible if I do the LCMS for that?
LCMS will give you, that's what I say, that if you do, and then of course if you check with the library, you can get a similarity index of that particular, because prussic acid and gallic acid, all these things, and all these things, all these have a library, I think, the spectra. So you can
that should be with
from the library, and then you would say check with your samples, and then you can find out from there, or you just take your samples as the output, and then check with the literature that are you getting those fragments related to this one. Once you get those type of fragments, definitely it's confirmed that you're but maybe the quantity is low. Okay, but this is the beauty of mass spectra. Even the quantity is low, still it will be detected, and you can do just like I show you that single ion monitoring. So we can choose that particular fragments. Is it whether it is present or not? They will only track those few ions. This is also the beautiful thing about. And you can do the same thing. You can when you do the scan, after that all these things will be there. You can just do the analysis, not have to run the sample every time. Is it by using so you have to be a bit sit together with your this application chemist, or those are expert with the program. Is it different instrument has a different program, and also the program setting, once you are applying this all what I say, that you have to choose this properly, so that you get the proper informations are recorded, and so that you have to have a proper training on that how the application the software is utilized, because software is controlling everything nowadays. You don't do a particularly for this LCMS. Software has so many things, and then you have so many things. That's why you have a separate training for software. One training is to instrument, how to run the instrument. Another training is to how to get the software, and then that is also not complete. Okay, so that's why I'm telling you to work closely at this time. My experience I'm sharing with you, that always have a good rapport with the application chemist for this. What instrument you are using? Which company? Agilent or?
We don't have it here. I would like to send it to Malang, to East Java. So Brawijaya University, they have it, but I still don't know what is the.
I will ask you, Dr. Ikwan. Especially, I always ask my student, because now because it become a trend. During our time, we used to go and make friendship with the those having the instructor. That means the person in charge, the science officer for GCMS or LCMS. We go and make friendship with them. We sit together with them. Because the one is that whatever you are learning from your book, that guy has learned from his experience. Okay, so I will suggest you, if you have the sample, better take some time off, or go to that place and then see yourself how the samples are running. Because sometimes what I see for our student now, it become a trend is, okay, the supervisor has the money, okay, I send it to UPM, and then they get the result only. They don't even know how the instrument look like.
Yeah. True.
Forget about the discuss about the sample. So they don't get the idea. They says, okay, Dr. Alfi will help me to do these things. Okay, Dr. Hilal will help me. Okay, they are becoming very dependent on the virtual. They become very virtual. So if you ask me for that is possible if you can go to that place and spend some time to see the analysis, to understand the thing, then I bet you get a better understanding that what you should do, what you are looking for, and how it can be done. Because if you are in front of that computer or that instrument, then you talk to this guy, then this guy will suggest you. But when you do the email or you just send the sample, can you analyze for me? You will just do a routine analysis and send it back to you.
Yeah.
This way you can do a diagnostic. That's why the diagnostic lab, they can say, okay, I want the glucose, sodium, potassium. Okay, they will do it for you. But for research, I think it's better that if you can take some time and if you have a friend there, then spend some time and then book. Ask him that, okay, I'm coming for 1 week. 1 week I want to be always with you.
Yeah.
You run in front of me. You show me what are the things.
That was actually.
That
was actually the plan if COVID didn't struck us. That we would like to go and visit IIUM to see.
Yes.
To see the lab.
Very sorry for that. Yeah, COVID has actually make our life like really very difficult.
Yeah. Yes.
Anyway, Dr. Ikhwan, if we have any help, please let us know. We'll try to help.
Yeah.
I think Dr. Alfi is quite experienced in natural products. I think he can help you a lot, inshallah.
Inshallah,
so, please take anyway, for the students, I think I will let them some time to read and digest. Okay, and to understand, because I know this is a very crash.
Exactly. They some of them don't have really an idea what is actually this thing.
Yes. But I really thankful to them. They have the patience to listen to us.
Yeah, but to my opinion, but to my opinion, this is very interesting because biomedical science that we have to be really ready for all new things, all novel things.
Especially you see in this COVID, the frontliner are biomedical researchers, biomedical scientists. They're the frontliner. Doctors are helpless. They cannot do anything now. Is it? Always they take the opportunity, but now they are looking at the biomedical scientists. Is it? Microbiology, biomedical science, or this virology. These people, they are looking at them. Is it? Biochemists. Because they are helpless unless we give them some solutions. And this is a very big, good combination that we have the chemists, we have the biomedical, all these things. Because I have some work with my friends, those are pharmacologists and biomedical science. Okay, but when they also get stuck when it comes to the instrumentation and analysis, they get stuck. Is it? They are very good in PCR, all these things. But when they come to that quantification or qualitative, all this, they get stuck because their thinking doesn't align with this one. And some of them, I'm saying that they are very good, they learn, but they always try to work with us, and then we also try to understand their issues, and we try to help them, whatever. So it's a very good combination because you can get a very authentic result. Is it? Otherwise, the results are not very complete. They say, I say, okay, I am a QC in charge for my pharmaceuticals, and I have a microbiology lab in my pharmaceuticals, and I am in charge of that as well. But if I say I am expert on microbiology, I'm doing some routine work there, but I'm not a researcher in microbiology. So I have to consult with the microbiologists, those people that, okay, what should be the way. So that's the same thing. That's you have to, these things actually that we are dealing with this. So we know ins and outs and other things and weakness, other things in there. So maybe we can be of more help, inshallah, I think so.
Yeah. Okay. The most important thing is speak up if you have problems. So I would like to say to the students,
don't feel
if you are stuck or if you don't understand, don't keep quiet. If you keep quiet,
no, again, I saw some of the researchers, they're very arrogant. Arrogant in a way that means they say, okay, I don't have any problem. But when you look at his work, you feel like he didn't really address the issue properly. He's just trying to get his name. Is it? But when you look into it, you are not really happy that, okay, but it is, we try to be humble. Yeah, I am not expert. Can you please suggest me? So it's okay, no problem. So any biomedical things I can, of course, ask Dr. Ikhwan, can you help me? I'm not sure what is this. Can you explain to me? And I will ask you a lot of questions. Is it? Because I want to get myself clear.
Yes.
So that should be the way. It's no harm that says, I don't know. I'm not supposed to know everything in the world.
Yeah.
That is the
Yeah,
most stupid
true.
thing that
Yeah.
if I have that type of attitude, that I know everything. Yeah. Of course, I
Yeah.
don't know. Even my
Yeah.
subject also, I don't know a lot of things. So we
Yeah.
have to be
True.
humble. We have to be humble.
So yeah, that is. Yeah,
As
that
I
is
say, very
actually
important that you should
the
speak up. That means you should be humble. That you say, okay, I don't understand this. Please, can you explain? That's the humble way you do it. That you are saying that I don't know. That not many lecturers also doing this. Especially when I go for thesis defense or other. Sometimes I feel like these lecturers are like asking the question the student just to make the student difficult. I don't know why they do. So
Yeah.
I think I also not agree with this type of arrogancy. I think, yeah, we will, you know that students and all these things, and then you don't know. Okay, so you speak up. It's very important. I think we should do that.
Yeah.
Okay.
Okay. Yeah. So I think
Yeah, I
yeah,
will
we
try
will
to
keep
send this by today.
contact
This
with
slide
Dr.
today.
Hilal.
Okay.
Yeah. Yeah. Dr. Hilal will still be in our group. So
Inshallah.
Dr. Hilal, you will be officially our collaborator now.
Inshallah. Thank you very
So
much.
then
Thank
we
you.
will keep in touch, and
Yeah,
very
I'm waiting to
interesting
visit
things, I believe.
Sumatra.
Inshallah, when COVID
I'm waiting.
finish, yeah, we will
Let
arrange
COVID,
sometime.
let the COVID finish. Inshallah, we'll visit or please come to UAE. Inshallah.
Exactly. Yeah.
Mm.
Yeah. So I think thank you very much, Dr. Hilal. Jazakallah khair. So we have to finish our lecture, the 8th session. So next Saturday, inshallah, we will continue again with Dr. Alfi with another topic, I think. And then, yeah, thank you very much for your attention. Thank you very much, Dr. Hilal, for the knowledge.
Okay.
Very useful and open a new horizon actually for us, even though it's difficult. But as German people say, everything is difficult at the beginning. So when we get through that, yeah, it will be easy. Yeah. So we have to do baby step first, and then afterwards we run.
Yeah,
So if
inshallah.
we run directly, then we will fall down.
Exactly.
Yeah. Okay. Yeah. Thank you very much for all. So wabillahi taufiq wal hidayah. Assalamualaikum warahmatullahi wabarakatuh. Good day, everyone. Stay healthy, and then don't forget to keep the health protocol everywhere. Yeah, because the COVID case now is keep increasing. Yeah.
Everywhere.
We have 30% case positive last week.
Okay.
Okay.
Thank you very much.
Yeah.
Jazakallah khair.
See you.
Assalamualaikum warahmatullahi
Yeah.
wabarakatuh.
Thank you very much. Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam.
Okay.
Sama.
Ya. Oke, saya Livia.
Pakai kepala deh.